So let's jump into chapter 3. Start chapter 3 with a big word, stoichiometry. It simply means, I think it's from the German. So, except for the metry part, I mean, the metry is like a Greek suffix. Stoichio, I think, comes from the German. Study of quantities, things that can be counted. But that's just the tip of the iceberg. There's a whole lot more we can get to there. Well, I guess that makes sense. Stoichiometry. All European languages were influenced to some extent by Greek and Latin. I never did study Latin, though. A lot of kids in high school took Latin, I think because they wanted to be doctors or lawyers. And at that time, back in the 70s, you had to know Latin or you couldn't get in their schools. Now I don't think you have to. Okay, so that's neither here nor there, except that to the definition of stoichiometry. We're going to put some meat on the bones here in a minute. First thing we need to do is recognize, revisit the fact that we can't see what's happening at the microscopic level. Everything that comes to us is macroscopic through our senses, and but we've got to get a handle on what's going on in the microscopic level, because that's where the action is. This atom, this molecule, that molecule, they're interacting. It's not something that we can easily account for. There are some instruments now that are so fast and specific they can watch the reaction atom by atom. But you're talking about millions of dollars. And this is a community college. So we'll go back to the old standby, the old-fashioned way. And the concept here is counting by weighing. We have the devices, we can readily weigh things. We need to make a connection between what that weight means for the numbers of atoms or the numbers of molecules that we're weighing. Okay, that's the connection. Yeah, atoms are too small to count. We treat the objects in our counting procedure as if they were all identical. And for our purposes, they are. What we need is to make the connection between counting and mass. We need a conversion factor that goes that includes mass and numbers of things. Our conversion factor needs to be that mass per numbers of things. Then if we weigh something and we know what the conversion factor is, right, for every one of these, it's going to weigh that much on average. Okay, if we do that, then we can use this as a conversion factor. When we weigh something, we can convert it into numbers. Right, that's all. Conversion factors are quotients. And since all conversion factors are equal to 1, right, if we need to, we can just flip it. Okay, now I got this is our example. We want to, actually it's an estimation of the number of marbles that are in this jar. That this pile of marbles weighs 394.80 grams. So rather than count all the marbles, we're just going to take a random sample of 10 of them and get the mass of those 10. And that way, each marble should weigh 3.760 grams per marble. Right? is divide by 10. That'll give you the mass of each marble. Now we have our conversion factor. And what we can do now is start with 394.80, 394.80 grams. That's the total mass. And we need to convert that by canceling the grams, numerator, denominator, and leave us with marbles. So that means this needs to be flipped. Each marble is 3.760 grams. That cancels grams and leaves us with marbles. So if I do my math right, we should estimate 105 marbles in that jar. Okay, that's what we mean by counting by weighing. Now we're going to take this example and try to use it to count atoms. All right. We can't weigh individual atoms, right? That's the part of this example that we can't do in real life, right? We can weigh 10 marbles, that's easy. But when we try to weigh 10 atoms, it's just, we don't have a balance sensitive enough to do that. So what we're going to do is we're going to assign a standard mass for a representative isotope, what an isotope is, right? Like carbon-12, that's where we're headed. Carbon-12, right, with 6 protons and 6 neutrons, we're going to assign a fixed mass to that isotope, and everything else will be compared to that. All right. So that's our standard, and we're going to say that it's equal to this one atom of carbon is equal to 12 atomic mass units. Okay. This is just one atom. One atom of carbon-12 is 12 atomic mass units. And we can take this out. This is like the exact numbers, right? It's not limited to the number of significant figures. It just goes on forever. 12 atomic mass units. And everything else is compared to that. So even another isotope like carbon-13 will not be a whole number. Its mass will be compared to that. Now you're probably wondering, how do we compare that? If this is one atom, how do we compare 2 atoms, right? Okay, we're getting there. We need to expand this idea into the realm where we can actually weigh them. Okay, and we're getting there, I promise. Your book is going to say U for atomic mass unit, but there's a unit, actually there's a Greek letter that's like this, which is mu. And it's easy to equate that or mistake it for that U that they like to use. That's why they've got U up there. I like AMU. There's no way to misinterpret that one. Okay. So next step, after all the other atoms are compared to this one standard. Originally, the standard was oxygen. They said oxygen atom is 16 atomic mass units. The problem with that is it's difficult to purify and handle oxygen because it's gas. So carbon, you can find it anywhere. Anything that's ever been living, you can just char it down, separate. Well, it's tedious, but it's easier to do than oxygen, and separate the carbon-12 atoms, and then you can get a mass of those isotopes. I think I've got a slide in here that shows you how you separate them. It's a mass spectrometer. Now, we have to recognize that all elements in nature are a mixture of 2 or more isotopes. Right? So carbon is going to be a mixture of carbon-12, Next most abundant is carbon-13 with 7 neutrons. And then carbon-14 is radioactive. All right, so we don't consider it too much. I mean, if we were in the business of doing this for a living, then yeah, we'd have to consider everything. But we're going to focus on these two because they're the most abundant when we continue our discussion. And what we've determined with using one of these mass spectrometers is naturally occurring carbon is 98.89%. 98.89% is that isotope. Okay. And carbon-13 is 1.111%. So if we add those together, that should be 100%. And this is such a small fraction, you know, it's like this. We don't even consider it, at least for our purposes. Okay.
That's because carbon is typically diatomic.
I'm sorry?
That's because carbon is typically diatomic, right? Because it's carrying around, because it wants.
No, carbon's not diatomic.
It's not, okay. Okay.
No. Start with nitrogen.
Okay.
Well, hydrogen and invert your L. These guys right here.
Okay.
They're diatomic. Now, certain allotropes of carbon, different forms of pure carbon, you can get combinations, right? Diamond is like carbon to the diamond is like this. Right? It has as many carbons as you want. I mean, a perfect diamond, a cut diamond, has no flaws in it, is a single molecule. It just has lots of carbon atoms. Graphite is like plate structure, and it's each one of these lines where the lines meet is a carbon, and they're just, let's see if I can do this. That, and it just goes on and on. The plates, and the plates sit on each other, and they're not covalently bound to each other. They're just there's just the London dispersion forces holding them together. That's why they can slide past easily. And graphite is a very good lubricant for that reason, because you put pressure on it and it just like that. But it's not wet. It doesn't pick up dust. So we used to have these little metal cans with a long, thin tube when I was riding motorcycles. And we'd stick that tube down our cable guides and squirt the graphite in there to keep our cables moving free. And then there are others like nanotubes. They're like this structure, only they're curved like that, and they just go on. And then my favorite is the buckyball, Buckminster fullerene. It's 60 carbons in a sphere, attached in a sphere, kind of like that Epcot Center thing. Not exactly like it, but it's the idea. So you can have allotropes of these, and they're not diatomic, but they're multiple atoms connected. So what we need to do is, for our purposes, we're not going to be able to work with isolated pure isotopes. We have to work with what nature gives us. So we know what the relative abundance of each one is. Now we need to calculate a mass unit for the average carbon. Now we're getting to the average marble. The average carbon is going to be a weighted average of carbon-13 and carbon-12 for our purposes. I mean, there are a number of other isotopes that figure in there, but they don't matter to us so much because we're only going to be using atomic masses to about the second decimal point. All right, so, and you'll see on your periodic table These guys have 4, 6, 8, 10 decimals. I mean, that's not going, 2 decimals, that table's going to be good forever. Okay, so how do we get the weighted average? It's kind of like calculating your grade point average, right? This class, the lecture is worth 3 hours, 3 credits. So if you get an A in this one, that's 12 units that you carry over. And if you get an A in the lab, that's only 1 unit. So it's worth more to be in this one than it is in the other one. This value is worth more because it's more abundant than this one. So the way we deal with it is we take this 98.89%. Well, actually, we're going to use the decimal equivalent so that we don't have to divide by 100. 0.9889. That's times 12. And then whatever that is, we're going to add to that the decimal equivalent of 1.11%, 0.111 times and 13.0034. And these are atomic mass units. Notice that this one is 12 exactly. This one's not, because it's related to that one. It's based upon this arbitrary value that we gave it. So this is that none of these other isotopes are going to be whole numbers. Never. So we multiply this one times that. This is the contribution of that isotope. This is the contribution of carbon 12. And then whatever that is, we add it together. And let's see if I animated it here. Yeah, that's an exact number. Rounded off to 2 decimal places, 12.01 atomic mass units. Right? Now, if you go out and sample naturally occurring carbon and you subdivide it and isolate it and you look at all the carbon atoms, are you going to find any carbon atom that have that mass? No. It's a weighted average, it's just average value. You won't find any isotopes of carbon with that mass. It's the average value that we can use because now we don't have to consider the isotopes. Right? We just know that on average, that's what our mass of carbon atoms weigh. Each one would weigh about that much times whatever. Let's see. Okay. Well, I stole my own thunder. There it is on the slide. Okay, this is a schematic of a mass spectrometer. All it's doing is separating isotopes. If you have a pure sample of naturally occurring carbon, say, we'll stick to carbon, then you need to get it in the gas phase. So that's what that heater is on the left. You just vaporize it. In a non-oxidizing atmosphere, you don't want to turn your carbon into carbon dioxide. Right? We want to heat it in an inert atmosphere. And then we shoot it into the instrument and we give it a charge. Right? If it's got a charge, now it will respond to electrical or magnetic fields. You know, it'll curve one way or the other. But we want to collimate the beam, and we want to accelerate it at the same time. So what you see there are those holes are bigger than they should be. These 2 plates are they generate a negative field because our carbons are now positive ions. We've stripped electrons off of them, made them positive ions. Okay, so they go through these slits, and these are negatively charged. So they go like that, and most of them crash into those electrodes, right? But those that are right through the center, they will pass through the center of this one and through the center of that one. Those are the only ones that come out straight. This beam is starting to diverge too soon. It doesn't start to diverge till it gets down here. Then we have this magnetic field, and we know that moving charges in a magnetic field feel the influence of that field and they bend. Okay. So in this case, we're bending them that way, which is neither here nor there. It's one way or the other. But the ones that are bent the most, since they all have the same charge and the field strength is the same, then each one of the ions feels the same push, the same force. Okay. The heavier ones, the carbon 14, the carbon 13, they feel the force, but they don't bend as much because they have more inertia. And the lighter ones, the 12s, they bend more. So the 12 is going to be at the top, and then the 13 and the 14. And I think there's a carbon 11. It bent more. But that's the idea behind the mass spectrometer. And there are a number of ways that you can achieve this separation. This is a good schematic. There are cheaper ways to do it. The mass spectrometer I had attached to my gas chromatograph was not a magnetic sector. This is called a magnetic sector. Mine was a quadrupole, which is another design that does the same thing, but for a lot less money. Okay. So that's how we're working our way toward standard masses for atoms so that we can count the atoms simply by weighing them. Okay, we're on that journey. Now, for this problem, an element consists of 62.6% of an isotope with 186.956 units. Let's go ahead and put that up there. 186.956, 186.56 atomic mass units, and its abundance is decimal equivalent, 6260. Okay, that's its contribution to the weighted average. And then the next one is 184.953. 184.953 atomic mass units. And its abundance will be in the neighborhood of 3740. 740. Okay. Now all we have to do is carry those out and then add them together. And if we do that, there's our animation, then we get a value of 186.2 atomic mass units. Okay. Now, what's that element? We know if we have some way to find the number of protons, that's easy. The atomic numbers. That will tell us the number of protons, and that is definitive for an element. But we don't have that. But one thing you'll notice is as the atomic numbers go up, the masses go up too. So we want to find one that's close to that mass, 186.2. You just start from top to bottom, left to right, and go till you get 186.2071 is rhenium. That's the element. Okay. Now we're going to make the connection. So if I get that, we're going to make the connection between these masses of individual atoms to masses of numbers of atoms that we can actually weigh. So we need lots of atoms. We need a huge amount. That's where this unit of the mole comes in. Right? It's just a number of things, the mole. And it's derived from molecule, mole. And they didn't pull it out of thin air. I mean, the value itself is determined by experiment. And the mole at the present time, the value we're going to use is 1 mole. And that's the abbreviated mole there. Just drop the E. is 6.022 times 10 to the 23rd. In our case, we'll just say atoms, but it could be anything. Atoms, molecules, ions, chickens. I mean, a mole's a mole's a mole. The standard, of course, is still carbon-12. And what we're going to say is 1 mole of carbon-12 atoms equals 12 grams. Now we're getting closer to reality because we've got a mass that we can actually sink our teeth into. Okay, that's called Avogadro's number. Now, Avogadro didn't think of that number. It's named in honor of Avogadro because of the work he did that allows us to get this far. Did we get the if you have two containers of exact same volume? We did that one. Yeah, that's Avogadro's contribution. And what it allowed us to do up until Avogadro's work, and by way of his student Cannizzaro, chemists and physicists of the late 19th century were now able to make the connection between masses of reactants and numbers of atoms and molecules. Up to that point, they only knew masses. It was kind of like a recipe. They had kitchens. They're big chemical factories, but they're no better than kitchens because you measure out a certain amount. And if something goes wrong, like if your cake goes flat or your souffle goes flat, you don't know how to fix it because you really don't know what you're doing when you're just talking masses. Right? When you're talking numbers, now you can say this many molecules of methane come together with this many molecules of oxygen and make this many molecules of carbon dioxide and water. Now, once you understand the numbers game, then you have a way to fix problems. Okay. And Avogadro made that possible. Okay. So for that isotope, that's what its mass is. But for the average carbon, you know, the naturally occurring carbon with its average mass of 12.01 atomic mass units, 1 mole now of just any carbon that we pull out of nature, 1 mole of atoms, since it's an average of 12.01 grams, 12.01 atomic mass units, now it's 12.01 grams for 1 mole of carbon atoms, and we don't care what the isotopes are because that's been taken into account for us already. Okay, so there you have it. 1 mole of carbon equals 12.01 grams. So if you take a sample of pure carbon, then you can use the conversion factor. Remember, all conversion factors are equalities. 1 mole divided by 12.01 grams, or 12.01 grams divided by 1 mole. That means if you have a sample of, say, 100 grams of carbon, and you want to convert it to moles, you just cancel the grams and leave you with moles. Excuse me. Yeah, that'll leave you with moles, 12.01. Then if you want to know the number of atoms, you use that conversion factor. Let that sink in for a minute. What that allows us to do is use these values. These are the weighted averages, and they can be interpreted as either this many grams per mole of krypton, or this many grams per mole of aluminum. Or you can say each atom of krypton is 83.7982 atomic mass units on average. So you use it either way. That's the beauty of this concept of the mole. That value can be one or the other, whatever you need. Most often we'll use it as grams per mole. So just to hammer this point a little further, why is 12.01 and not exactly 12 grams? Because it's a weighted average. All right. Number of iron atoms in 4.48 moles. So which conversion factor we need for that? 4.48 moles of iron is equal to how many atoms? We need a conversion factor. Moles on the bottom, so they'll cancel, and atoms on the top. All right, 1 mole of 2 times 10 to the 23rd atoms. So that times that will give you your answer. And by the way, it doesn't matter if they're iron atoms or not. If you got 4.48 moles of any atom, it'll give you 2.70 times 10 to the 24th atoms of whatever you started with. Let's see. Now this is a conversion factor, so it's an exact number. This is the only one that determines the significant figures of your answer. 3. Okay. So from the periodic table, we just look up there, say nitrogen in this example. It's reported as 14.00672. I always round off to 2 decimal places. It's easier to deal with it that way. And it's plenty good for our calculations. So rounded off, it's 14.01 grams per mole of nitrogen. Right, just read it off the table. Okay. Next step. The world isn't made up of free atoms. The world's made up of compounds. Right? So how do you use this information we've given you to talk about compounds? All you have to do is say how many atoms are in the molecule, and that's the number of moles. If you have, look at it this way, 1 mole of water equals how many moles of oxygen? Right, there's 1 mole for each molecule, so there's 1 mole of atom for the molecule, so there's 1 mole for a mole of the compound. So that's 1 mole of oxygen. How about hydrogen? 2 moles, right? 2 moles of oxygen, hydrogen. Okay, so if we want to calculate what we call the molar mass, how much does a mole of a substance weigh? What's its mass? All we have to do is add up 1 mole of oxygen, which is 16.00 grams. That's grams. And 2 times 1.01, which is 2.02 grams. So that's 2018. That's grams per mole of water. Okay. There it is. They didn't round off, I did.
Why does hydrogen, why is it 2.02?
Because there are 2 of them.
Oh, okay.
I rounded off to 1.007947 is 1.01.
Okay.
Times 2. Now let's do a bigger one. How about barium nitrate? Oh, I didn't mean to put that one in there. So barium nitrate, it's important now that we know how to count up the number of atoms in a molecule or in a formula, right? Technically, that's not a molecule because it's an ionic compound. Molecules are covalently bound. Water is a molecule. It's a single unit that acts like that. Ionic compounds Well, if they're solid, they're locked in place, but if they're melted or dissolved in something, then the individual ions separate and it's just a ratio of this ion to that ion. So we usually say formula weight rather than molecular weight. But we have one barium, right? We look over there at barium, which is alkaline earth down at the bottom, 137.33 times 1, right? Nitrogen is 14.01 for one nitrogen, but we got two of them, don't we? Right? So that's times 2. This is times 1. And oxygen, rounded off, is 16 times 6. Okay? They add all those up and you get 261.35 grams per mole of that formula.
So, I just make sure I understand correctly. A mole is the equivalent of one atom, or a mole is the equivalent. What did you say?
I'm not getting your question.
Hold on. I'll come back to it.
1 mole is 1 Avogadro's number, 6.022 times 10 to the 23rd. So if you want the mole of this formula would be 10 to the 23rd of those. And 1 mole of that weighs 261.35 grams. Because 1 mole of this weighs that, 2 moles of this weighs that, 6 moles of this weighs that. You add them up. All right. I don't know why I keep this slide in there. It's kind of a stupid slide. If you're thinking, maybe that's the point. If you're not thinking, then you'll get stumped. Which of the following is closest to the average mass of 1 atom of copper? Does 1 atom of copper weigh 63 grams? No. It doesn't even weigh 52 grams. So 10 to the minus 22 grams is the answer. If you wanted to calculate that, you would just say, all right, copper is 63.55. 63.55 grams per mole, right? And we want to know how much 1 atom weighs. So we want to get rid of the mole and replace it with atoms. That, right? Denominator, numerator, and the magic number is Avogadro. So 10 to the 23rd divided into this gives you that 10 to the minus 22. Okay, that's how much 1 atom of copper weighs. Oh, there it is. Sometimes I forget I've animated some of these. Okay, the number of copper atoms in 63.55 gram sample of copper. That's Avogadro's number because 63.55 is the molar mass. Right? So that mass represents 6.022 times 10 to the 23rd copper atoms. All right. Now let's complicate things. Which of the following 100 gram samples contains the greatest number of atoms? So we got magnesium, zinc, and silver. And silver. And 100 grams of each one. I think it has 4 significant figures. Yeah. Okay, we want to find the greatest number of atoms. Which one has the greatest number of atoms? Let's look at this from a qualitative standpoint first. Are they going to have the same number of atoms each? 100 grams of each. No, right? They're not going to have the same number of atoms. So one of them is going to be the least, one of them is going to be the most, and the other one's in the middle. So how do we tell how many atoms there are? Their molar mass, right? Molar mass. So if we want to convert to the number of moles, and remember the number of moles is a counting number. So if we're just comparing, we only need to know the number of moles. We don't have to go all the way to atoms. Just compare the number of moles and that'll answer the question. So this magnesium, and this is what I call Ford's assembly line. You set it up, you're doing the same calculation each, you're just putting different parts in it, right? While the car moves down the assembly line. So for magnesium, we want to cancel grams, leave us with moles. So magnesium is over there, it's 2431, isn't it? 24.31. Zinc is a lot heavier. It's a transition element, and it's 6538. 6538, right? That's correct. We're getting rid of the grams, leave us with moles. And then silver. Silver is even heavier. 107.87. There we go. Okay. Now, since we're just comparing, we don't actually have to calculate the number. We're comparing moles. Is this one, well, we kind of do have to. This one divided into 100 is about what? 100 divided by 25 is 4, right? So it's a little bit more than 4, approximately 4 moles. How about this one divided by 65? If it were 50, it'd be 2 moles, but it's bigger than that. So it's less than 2, like maybe 1.8. And this one is less than a mole, right? Less than 1 mole. So that's the greatest number of atoms. The greatest number of atoms is going to be this one. It's the most moles. The point of this exercise is to show you that the number of atoms for a given mass is inversely proportional to its molar mass. Because if each atom weighs less, it takes more of them to make that mass. That's the whole idea. Okay. All right. Now, let's see. I put them in different order. Silver, zinc, and magnesium. So let's do this. Silver, zinc, magnesium. And let's see. Silver is 107.9, 107.9 grams. Zinc is 70 grams. Right. We can leave that one there because zinc was in the middle before, wasn't it? And magnesium is 21 grams. So this is going to change to that value. And this is going to change to the silver value, which was 107.87. Okay. So we want to put these in order from greatest to least numbers. Since we're ordering again, we don't have to get exact values. We just need to compare them to 1 mole. This is essentially 1 mole, right? This is greater than a mole. And because the denominator is smaller than the numerator. And this one's greater than the numerator, so this one's going to be less than a mole. So if we want to put them in order from greatest to least, the greatest is zinc. right? And the least is magnesium. That puts silver in the middle. As far as numbers of atoms go, that's the order. Now, I'm trying to offer you quick ways to solve problems. Once you know what the question is, maybe you don't have to go all the way to the end of the line to answer it. Okay. Here we go. All right. Now, let's make things more complicated. Why don't we? Because the real world is complex. We're trying to ease into it here. 100-gram samples of each of the following. We want to rank them greatest to least number of oxygen atoms. Okay. Now, it should be obvious that we can't just look at that and say what it is. It's not going to happen. Right. Right. Maybe in anatomy and physiology, somebody asks a question, you can bam like that. But not in the hard sciences. You got to work the problem. So we got water. Let's set up our assembly line. Laughing gas, C3H6O2. Yeah, I think that's propionic acid, and CO2. Okay, we got 100 grams of each one. Set up our assembly line. And start our conversions. All right, what is this going to tell us if we get rid of the grams and leave us with moles? Right? How many moles of what? If we calculate the molar mass for each one of these compounds and convert it, what moles are we calculating? Moles of molecules, right? We haven't got to atoms yet. Okay, so the first conversion is grams to moles of molecules. Okay, so we need a conversion factor. We did water earlier, 18.02. N2O, 14.01 times 2, and then oxygen. Times 1. So that's 2802 add 204, 4402. Okay. C3H6O2. So we need 3 carbons. We need 6 hydrogens. And we need 2 oxygens. I'm not going to try to do that one in my head. There was a time when I might have been able to, but not anymore. 6.6 and 32. So this one's 7409. 74.09. And CO2 is 12.01. 2 times 16 for oxygen is 32, right? So that's 104. 44.01. There we go. Now that gives us moles of this formula. But these are all molecules, so we can say molecules. There are no ionic compounds in there. So the next thing we need to do on our assembly line is convert moles of molecules, mole, to moles of oxygen. Okay, you need a conversion factor that'll do that. Okay. This is going to help. This exercise helps you understand what we're going to do when we're actually dealing with a balanced chemical equation and we want to know, and I put this into the equation, what comes out. Okay. So what's the ratio here? 1 oxygen for every 1, right? 1 to 1. This one is also 1 to 1. This one is 2 to 1. And this one is 2 to 1. There we go. So we cancel the grams to get moles of molecules, cancel the moles of molecules to get moles of oxygen. All right. So now, that was the thinking part. The rest is number crunching. So if I take 100, 100, divided by 18.02, and times 1 is 5.55. This is moles of oxygen. So I go back to 100 again. Yep. And divide by 44.02 times 1 is 2.27. Actually, I could go an extra significant digit, but I don't need it really to answer the question. And let's see, 100, put that back in there. 74.09 times 2. Divide by it, then multiply. This is 2.70. And 100 again, 44.01 times 2. And this is 454. Okay. So now we can put it in order from greatest to least number of oxygens. The greatest is this one. Right? That's the first one. Second one is this one. Third one is this one. And the last one is that one. Okay. That's my Henry Ford model. Okay, there it is. All right, this is just a reinforcement for problem solving. When it says, where are we going? That's just, what's the question? Yeah. How do we get there? That's the scheme that you devise to solve the problem. Sometimes it's just a single step, like a conversion. If we wanted to go from here to something over here, we just use 1-step conversion. That's it. It's all over. But if the question requires, if it's more complex, then you may have to break it into pieces and solve the individual pieces and bring them together to get your final answer. Always keep the final answer in mind. I know it's hard to do because I get lost too on the board sometimes. But when in doubt, go back to the question and make sure you're on track. And then once you've got your answer, ask yourself, does that make sense? Like, well, does this make sense? 100 grams? Yeah, I think it does. If that were 50, it'd be 2. 70 would be about 1.3 or so, and then times 2. Yeah. Okay, so estimation helps out. If you can estimate your answers and just satisfy yourself that you're not completely off the wall. I don't think I told you guys this story. A friend of mine was in, when I was living in Louisiana, he was a mechanical engineer student at LSU. You know, they build stuff. He borrowed a spring gauge from me that had like hundreds of pounds available, and used that to design a cam for a compound bow. That was his project. And he told me stories about some of the students in his class. He said it just boggles the mind. They'd study something in this chapter, and then come test time, the question would require that you use information that you learned in this chapter, the one before. They would plug numbers like square pegs in a round hole and get the wrong answer and wouldn't have a clue that they were wrong. Or if they knew that they were wrong, they didn't know how to fix it. because they weren't using all the information that they'd been given up to that point. He said it just amazed him. Those students either corrected their course or they failed out. That's the only two options. Okay, now let's see. Yeah, okay. I got another hour, don't I? We're good till 4, or is it before 4? 3:50. 3:50. Okay. I'll try to be quick, but not so quick that I'd leave you behind. Because each one of these progressive steps we're taking, they build on each other, and they're building toward the practical ability to solve chemical problems. The next thing we need to know is, let's answer the question. How does a bench chemist tell me, if I give them a pure sample of a compound, how are they going to report the results, the composition of that compound in terms of elements? I want to know how much of each element is in my compound. Most often, they report it as mass percent, right? If I give them 10 grams and they isolate 1 gram of, say, carbon, then that would be 10%, right? Okay. So they would report it as 10% by mass. So I think I mentioned this before. Percent is a dimensionless number. It just means parts per 100 parts. If you just say percent, there's no way to know how you got there. So we say mass percent, that means parts in grams per 100 grams is parts. Grams per 100 grams is mass percent. Or we could say, sometimes it's written this way, like that, mass. That's better, because some percents might be mass volume or volume, like alcohol. If you buy wine that's 15% ABV, right on the bottle, alcohol by volume, that's percent volume. So it'd be like 15 milliliters of pure ethanol per 100 milliliters of wine. That'd be 15% ABV. I think beer standard is what, 6.4? Yeah. And there was a time in this country when you couldn't get 6.4. They knocked it down to 3.2. You know, they call it near beer. You had to go north. Yep. Yeah. Okay. Or make it yourself. I had a professor as an undergraduate who he was an invertebrate zoologist, studied insects and stuff like that. He lived like 20 miles out of Atlanta. And we went to his farm occasionally. He kept goats. He was using, at that time, the only way that you could get antibodies, custom antibodies, was for your customer to give you the antigen and you inject it into your goats and then isolate the antibodies from your goats. Now they can do it monoclonal with cell cultures. But back then you had to use live animals to do it. And he had that business on the side. So out at his farm, he had goats everywhere. But he used to walk his farm. And in the Georgia sun, it's hot. So he would make his own beer. And when he bottled it, he would put an extra teaspoon of sugar in it and cap it. And apparently he figured out how much he could put in there before he blew the bottle. But when he cracked it open, I mean, it wasn't 15, it wasn't 6.4, it was more like 15 or 16% alcohol. That way he could ice it down and it would stay potent through his entire walk. Okay, I remember another experience when I had his class. I didn't have a clue what the answer to a question was. So I made something up. He had this stamp. It was a rubber stamp with the figure of a bull. So he hit his red stamp pad and stamp your problem. That's a bunch of bull, you know. Mass percent of an element. Okay, it's simple, really. You just need the mass of the element that's in the compound and the mass of the compound from which that mass of element was derived, the total mass. Okay, that's what that percentage means. Now you can do it two ways. You can do it like I've described, bench chemist. You do the analysis and you report the values. But we can calculate the theoretical amount from the formula, right? The compound formula. So in this case, iron 3 oxide, which is type 1, 2, or 3 compound. Type 2, yep, because we have multiple possibles. So we're going to have iron here, we're going to have oxygen there. Now, how do we reconcile this? Well, we know that this is 3 plus. Says so right there. And oxygens in ionic compounds are always 2 minus. Right? Because this is 0, 1 minus, 2 minus, 3 minus. Okay? So now we just have to balance those charges. Well, odds and evens, the best way to deal with it is cross multiply. So I'll bring this 2 over here and this 3 over here. That's 6 pluses, that's 6 minuses. We're good to go. So that's why the formula is that way. Okay? Light bulb goes on. What we're headed for is calculate the expected percent composition from its formula. Okay? And let me see if I don't want to steal my own thunder here. Well, that puts everything into a single package. Let me break it apart. First of all, let's say we need a uniform number of not molecules, but formula units. So let's say just 1 mole. If we have 1 mole of that compound, what mass do we have? We know how to do that, don't we? It's 2 times iron, which is 5585 grams per mole. So that'll be 0, 1 is 16, 17. Yeah. Like 111.7. Yeah. Grams. That's for iron. And oxygen is going to be 3 times 16 for each oxygen. So that's 48. Oxygen. Okay. So for 1 mole, we've got this many grams of iron, this many grams of oxygen. What's the total mass? There, 7, 9, 159.70 grams. So if we're going to do percent composition, the denominator is going to be the total. The numerator depends on which element we're after. In this case, I think we're after iron, aren't we? Okay, so we'll just put iron on top, right, times 100. And that's 69.94%. Percent iron mass. Notice that the bottom is the total. That means that this value is also included in that value. Don't forget to do that. Now that's the theoretical. If it's a pure compound and we're very good at our technique as a bench chemist, then we should come out very close to that value for percent iron with this pure iron oxide. That's rust. Okay. All right, 100 grams. What I'm afraid of is, let's see, 3.6. I'm going to go slides. Okay, I'll tell you what. We could spend time on this, but I'm afraid we're going to run out of time. So let me just tell you how you set it up. If you've got 100-gram samples of each of these compounds, like we did before, it's the same set of compounds, rank them in highest to lowest percent oxygen by mass. So you would just set up the calculation for percent oxygen, like we did for iron, and just compare them. Right? Percent oxygen. Right? You would say water would be 16 divided by 18.02 times 100, because one oxygen is 16 and the total is 18.02. And do the same thing for the rest of it. Then you compare the values. Now, if you want to see it done, go back to a previous video and just scroll down to section 3.6, and you can see me doing it when I didn't care if I wasted the whole afternoon or not. And what it doesn't matter is 100-gram sample. That's irrelevant. That's one of those items, that's blue smoke in a word problem, right? Remember, word problems are designed to confuse. So that's part of the confusion. 100-gram sample, who cares? I mean, if we're going to calculate the percent, we just go from the formula, right? The only time that I would be interested in 100 grams is if they give me grams of each one of the elements that we're trying to calculate. Then I might use 100 as the denominator. But barring that, just use the formula like we did before. Okay, so that's the order they should be in. Percent oxygen by mass. Water has the highest percent oxygen by mass. Does that make sense? Yeah, because it's mostly oxygen. Hydrogen weighs almost nothing. Okay, now we're going to use that information that the bench chemist gives us, percent composition, to determine ultimately the molecular formula of our compound, or the formula, the ionic formula, whichever the case, it doesn't matter. We're going to determine the formula from the percent composition by mass. We have to do it in two steps. One is the empirical formula. What that means is the empirical formula is the simplest whole number ratio of elements, of atoms in the element formula. Here, let me illustrate. I'll give you the molecular formulas for two compounds. Okay? This is benzene. Okay? Which is banned now because it's carcinogen. And this is acetylene, which you can get in the tank and you cut and weld with it. Yeah, welding gas. One of the welding gases. The simplest whole number ratio of carbon to hydrogen here is CH. 1 to 1, 6 to 6, right? Simplest whole number ratio. Same for this one. This is the empirical formula for both compounds. Okay, so we can determine the empirical formula from the percent by mass composition, but that doesn't tell us what the molecular formula is, because I hope this illustrates that these both have the same empirical formula. So the second step is we need another piece of information. We need to find out, we need to be given or experimentally determine the actual molar mass of the compound. Right? The molar mass of this compound is going to be 3 times what this one is. Okay, and I'll show you how to use that in just a minute. Okay, so we're given percent composition. I'm going to skip this. This is just a carbon hydrogen chain, and we put the sample in a furnace, we blow oxygen through it and burn it. And if we know that it only has carbon, oxygen, and hydrogen in it, then we can deduce the composition. The first absorber picks out the hydrogen as water. So we weigh it before and we weigh it after. This tells us how much water was. And then we ratio hydrogen to water and find out what actual hydrogen mass is. Okay. We could spend the whole class period on that. Do the same thing for carbon. And then if we know that it's carbon, oxygen, hydrogen, then we've got the carbon, we've got the hydrogen, and we know what the total sample weight was. So the difference is oxygen. We can't get oxygen from this train because we're blowing it in there by the truckload. Okay. So for this example, adipic acid, which is a fatty acid, right? Everybody's fats have some adipic acid in them. Remember you had the biology or anatomy and phys, right? True fats, they're triglycerides. They're a glycerol molecule with these three hydroxyls off the side, and you snag each one with a fatty acid, and that's your true fat. Well, we've got this pure fatty acid, adipic acid, and we want to determine what is its molecular formula. What is its actual formula? Carbon, hydrogen, and oxygen. So we start off with 49.3% carbon. I'm going to come over here like this. 49.3% carbon and 6.9% hydrogen and 43.8% oxygen. 43.8% oxygen. And that's by mass. Mass. Okay, what we've got to do first is get to a simple ratio of the closest that we can get to the whole numbers, carbon atoms to hydrogen atoms to oxygen atoms. Simplest ratio, right? It's the first step, that CH ratio. Okay, but this is in percent, right? We're stuck because we want moles. And we can't get to moles until we have grams, right? So here's the trick. If this is percent, I got a 100-gram sample, right? 100-gram sample. So what does that mean for carbon? Well, that would be 49.3 grams, wouldn't it? Okay. 6.9 grams of hydrogen and 43.8 grams. Now we can hit the ground running. We need to convert these to moles first. Right? So we cancel grams, leave us with moles, and you know what that means. Anytime you see grams and moles in a quotient relationship, think molar mass. So oxygen is 16, right? Just look it up. 15.999, 16 grams per mole. Hydrogen is 1.01, and carbon is 12.01. There we go. So I'm going to take these in steps, right, rather than string them out. Because it works better that way. I'm going to, let's see, 49.3 divided by 12.01 is 4.105. 4.105. And that's moles of carbon. 6.9 divided by 1.01 is 6.83. 6.83. And, yeah, okay. So 2 moles of hydrogen, and 43.8 grams divided by 16 is 2.738 moles of oxygen. Okay. I probably don't have to tell you that's not a whole number ratio. But it is the molar ratio in the molecule. You've got this many moles of carbon ratio to that many moles of hydrogen to that many moles of oxygen. So this ratio is true. What we need is whole number. So there's a rule in math that says if I do the same thing to each one, then I haven't changed the ratio. Say if I divide them all by the smallest one, right? Divide them all by 2.738. Then the ratio is still the same. So this is obviously 1, and 6.832 divided by 2.738 is about 2.5. Now we're going to start estimating, rounding off, because the values that I'm getting are very high. 2.495. That's close to 2.5. That's close enough for our work. And then 4.105 divided by 2.738 is 1.5. Okay, so this ratio of 1.5 to 2.5 to 1, we're getting closer. Now we would need to get rid of those fractions. So how do you get rid of a half fraction? Multiply by 2, right? So if I multiply each one by 2, I still haven't changed the ratio, but now I've got whole numbers. 3, 5, 2. That's the molar ratio of the empirical formula for adipic acid. Carbon, 3, hydrogen, 5, and oxygen, 2. Okay? Now, the molecular formula is either going to be that, or it'll be 2 times that, or it'll be 3 times that, or it'll be 4 times that. So the way I express that is here. That number propagated through here will give us our molecular formula. We need to find out what that is. Okay? So the way I do that is I need that other piece of information. Let's see, the empirical formula. There it is molar mass of the compound is actually 146 grams per mole. So I call it the molecular weight. 146 point, that's it, grams per mole. If I add up the molar masses for each of these atoms in this formula, I'll get what I call the empirical weight. Okay, so the EW is equal to 3 times 12.01 plus 5 times 1.01 plus 2 times 16. Right? So let's see, 12.01 times 3 and 5.05 plus, and then 32 plus. This is 73.08. 0.08 grams per mole of the empirical formula. This is grams per mole of the molecular formula. Now, if I multiply 1 times that, then the molecular weight we're saying is 73.08, but it's not, right? It's actually this one. What if I change this to 2, right? 1's out. If I change it to 2, then I've got 4, 10, and 6. And that would be twice this, twice that, or twice this. And twice this would be 143.08, which is pretty darn close. So within margins of error, we found it has to be a whole number. If we use 3, then it's going to be too big, right? So our N is equal to 2. And that means C6H10O4. That's the molecular formula. Okay, that's how it's done. If you're given percent composition by mass, and that's all you're given, well, in addition to the actual molar mass. Now, how did they get that molar mass? There are ways. Second semester, we're going to use one or two of them. Right. One is freezing point depression. The colligative properties that we investigate in the second semester are independent of the identity of the solute in a solution, of the stuff you put into solution. So you don't have to know what it is. You just need to know how many moles it is. And then you can calculate a molar mass. And then you give that to the person doing the problem and they can finish it, figure it out. There are other ways to do it also. Okay. So, erasing the clock here. I needed to spend time on that one because that's a very important skill to develop. And there are a number of other skills that you've acquired so far that go into doing this, like unit conversions. Right? In order to do this without too much trauma, you need to be able to do unit conversions in your sleep. Right? All right. Representation of a chemical reaction. So in the beginning, we're going to say the reaction only goes one direction. That's why the arrow goes from left to right. Reactants on the left, products on the right. We put the formulas for the reactants, as is. In this case, we've got one molecular formula and one diatomic oxygen reacting together to make two molecules, molecular formulas. Okay? Those formulas, once you write them that way in this reaction, those numbers, those subscripts are fixed. C2H5OH, you cannot touch those numbers. 2, 5, 1, and 1. Those are fixed. So the only way, if you're going to balance the equation, is through coefficients, numbers in front of each of the reactants and products. Okay. And if you write your reactants and products correctly, then you have a pretty good chance of balancing the equation. The whole idea behind balancing this equation is we go all the way back to Lavoisier. The mass of the reactants equals the mass of the products. And the only way we can do that is if the same number of atoms of each element is on the left-hand side as on the right-hand side. That's central to the whole prospect of balancing equations. This equation is balanced as written, and you can see, right? How many oxygens are on the left? 6 plus 1 is 7, right? On the right, you have 4 plus 3 is 7. So you can do the same thing for the carbon and the hydrogen, and you'll find that it's balanced. Have the same number of atoms of each element on both sides. And I'm going to show you how to do that in a minute. This can be interpreted as either what I just described as so many molecules, so many atoms on either side, or the coefficient can also mean so many moles of each one. So 1 mole of ethanol, C2H5OH, plus 3 moles of oxygen yields 2 moles of carbon dioxide and 3 moles of water. It works either way. Now, if you're going to do calculations, you think of it in terms of moles, because moles to mass is an easy conversion. You just need the molar mass of each one of these reactants and products, and you can go to town with it. Okay. This is just a cautionary statement. When we write the reaction that way, we are assuming our starting position is 100% conversion. Everything that's on the reactant side ends up on the product side. But that never happens in real life. That's a theoretical amount. If you can get, if you're in the industry, in the chemical industry, and you're trying to conduct one of these reactions, Sometimes 15% is a good yield. And then on up is better. All right. So we have to balance the equations, and I put it in prose here, but really showing you how to do it is the best way. I just put it in there so that if you want to go back and read and see, be sure you got the steps in line. That's fine. I will make this point though. There are some chemistry textbooks that are drifting away from this idea of balance the equation by inspection. That's what my chemistry book said when I was in school, right? That's a cop-out. When you tell your students to balance an equation by inspection, you're saying just bulldog it and just put every number you can think of in there until you get it right. And that's going to take forever. I've got a method for balancing equations. So the author just didn't want to deal with it. We're going to do that. I've got some helpful hints here, and one of the handouts has those helpful hints in print. And some equations we use the hint, and some equations we don't. Right? And I'll try to do a number of balancing acts so that you can see the different types of tricks that you can use to simplify the process. Sometimes what we want to end up with is whole number coefficients. But an intermediate step might be helpful to use a fraction to get to the balanced place, and then you get rid of the fraction to give you the whole number. And a lot of your hydrocarbon combustions, like this CHEM101, which is octane, right? It's in the gas tank. When you burn it, right, you try to balance the equation, right? Combine it with oxygen and get carbon dioxide and water. Trying to balance the equation, it's difficult to get there. And an intermediate step is to use a fraction. And then you get rid of the fraction. See, in the first one, we're balanced with that 25 halves. Then we multiply the whole thing through by 2 to get rid of the half. Okay. Once you got the ratio, then that's fixed. And anything you do to each one of the coefficients will maintain that ratio. So now we got 2, 25, 16, and 18 instead of 1, 25 halves, 8, and 9. That's one of the tricks. Another thing to consider is if your reactants have polyatomic ions in them, like this one has ammonia and phosphate, ammonium and phosphate. If they're on both sides of the equation and they haven't been changed, sometimes they get busted apart in the process. But if they haven't changed, we got ammonium on this side, ammonium chloride on that side, we got phosphate on the reactants and phosphates on the product. You can use those polyatomics as a balancing unit. You don't have to break them apart. Okay, and that really simplifies things. That's one of our examples. Let's come back to that. I want to do one. Let's do a simple one. Say, oh, there's no example. Okay. I'll just make one up. Let's say combustion reactions are fun. So let's take, say, propane. Right? You got a propane tank at home, you go to barbecue with it, or maybe you heat your house with it. I don't know. Propane is C3H8, right? 3 carbons and 8 hydrogens. Right? And if we specify the phase, this would be a gas. And then we're going to burn it in oxygen, right? Oxygen has to be diatomic, right? It's one of those diatomics. And we're going to say this is a gas also. And the complete combustion of hydrocarbons should give us carbon dioxide and water. Now, it could be, if we're doing this under standard temperature and pressure, this would be a liquid. But if we're doing it in reality, it's going to be water vapor. So we'll just do it that way. Okay, so there's your equation, and all the compounds and elements are written correctly. That's your first step, reactants and products. Now we do an assessment. How many are we starting with? Well, we've got carbons, right, on both sides. We've got hydrogens and we've got oxygens. That's all the elements that we're going to deal with. On this side, we're starting off with 3 carbons, 8 hydrogens, and 2 oxygens. But on this side, we've got 1 carbon and 2 hydrogens and 3 oxygens. Okay, so you can see at a glance that we're not balanced. Okay, so the first hint or trick is if you've got any single elements on either side, don't touch them until the end. Right? Don't put anything, don't deal with the oxygens now. Because if you save the oxygen till last, then when you put a coefficient in front of it, it's only going to change oxygen. If you save something else and like put it one here, now we got to deal with hydrogen again. So we save the elements till last. And then sometimes it just takes practice and you say, where do I start? If I can't make up my mind where to start, I just start at the top. Right? So we got 3 carbons here. We need 3 carbons on this side. We do it with a coefficient of 3. Then we reassess 3 carbons. Now we have 6 oxygens, 7 oxygens. There we go. Okay. So now I'm going to move to hydrogens. I'm not going to touch oxygens yet. Move to hydrogens. We got 8 on this side. We need 8 on this side. Hydrogen only occurs in one place. So if we put a 4 here, that's 8 hydrogens, isn't it? But now we have to reassess the oxygens. So that's 4 and 6 is 10, right? Last time I checked. Okay, now we can deal with the oxygens. How do we get 10 oxygens out of this? There you go. And now you can see at a glance, we're balanced. This is what I call my budget method. Right? This is the amount of money coming into the household, and this is the amount of money going out. Hopefully they're equal. If it's my household, you got this much going in and you got more going out. Especially with inflation, which is moderating some, but it's still hitting us hard. We're still living under the specter of the actually Obama's 3rd term. I think Biden was just a stand-in. Obama's running the show. And I won't go into details, but there's some evidence to prove that. Okay, so in this case, we didn't have to do anything but use that one trick, right? Hold the elements till last. Let's go to this one. And I've got it animated, so I won't have to put it on the board. I know it might be more useful, but it'll take time to do it that way. So we've got our equation written out. Our compounds are written correctly, right? Ammonium is a +1 charge. Phosphate is a -3 charge. So we need 3 ammonias to balance, and that's written correctly. We balance the charges. Calcium chloride, calcium is an alkaline earth with a 2+ charge. Chlorine is an halogen with a -1 charge, so we need 2 minuses to balance the 2 pluses. Similarly with calcium and phosphate, there we have calcium 2+ and phosphate 3-, so we do a cross multiply to get those. Okay, bring the 3 down from the phosphate and the 2 down from the calcium. And then at the end, ammonium is 1+, chlorine's a 1-. So you just need 1 of each. Okay, now we have our compounds written correctly. We need to do an initial assessment. Okay, so notice that we've got these polyatomics as balancing units, groups. because they don't change on either side. They're exactly the same. So we got on the reactant side, we got 3 ammonias, we got 1 phosphate, 1 calcium, and 2 chlorines. Okay. Then we go to the other side and assess 1 ammonium, 2 phosphates, 3 calciums, and 1 chlorine. And we can see that it's not balanced. So where am I going to start? Let's see. I don't have any single elements, so we can't use that trick. Maybe I just start at the top, or maybe I started with calcium. I bet I started with calcium. Yep. So that red 1 means this is my first step. And when you look at the worked problems, what I tried to do is, when balancing equations, was, let's see, let me find an example. Yeah, in these little circled numbers, that tells you the order of the operation. So look for the 1, and that's the first thing I did. Okay. The original's in color, but it's about 10 times the number of bytes, right, to do it that way. So I had to make it grayscale. Okay, so the first thing I'm going to do is take care of the calciums. I need 3 calciums on the reactant side because there are 3 on the product side. So there's my 3. And now I reassess. Okay. There's 3, and then the chlorines also change, right? They're going to be 6. Okay. So now, chlorines are too many. Am I going to go chlorine next? No. Yes, I'm going to go chlorine. Second step. So I put a 6 in front of the ammonium chloride, and that gives me 6 chlorines on the product side. And we do a reassessment. The ammoniums now are 6, and the chlorines are 6 also. So we got the chlorines balanced. Now the ammoniums are off balance. I'll go back to the reactant side and put a 2 in front of that ammonium phosphate. And that'll give me, here we go. That'll give me 6 ammoniums because the subscript is 3 times 2 is 6 ammoniums. And then 2 phosphates. There we go. And then the calcium, I forgot to finish the calciums off, so there we go. We still have 3 calciums. So 6236, 6236, that equation is balanced. Now I'm giving you easy ones in the beginning, because some of them can be really, really problem. I've seen some that I wouldn't even tackle. And a lot of chemists who have really very complex reactions that they have to balance will go to their computers, and they have algorithms that will go through it, and it just it's not so much logical as it is brute force. They just try every combination of numbers they can, and with the algorithm, and eventually come out with, it's just watching for when it balances. Yeah. Okay, this just illustrates the fact that these are all balanced. I think they're all balanced, but we prefer the simplest whole number ratio of coefficients. Right? Even though there's a balance, the best one is the simplest number, which is 2. Okay, I'm gonna have to skip this. I'm running out of time. This is what has changed. Atoms are following are true concerning balance equations. They be more than one true statement. All right, atoms are neither created nor destroyed. That's true. Right. The rest are false statements. This just hammers that point down. Once you've written your compounds, don't touch the subscripts. Right? Don't touch the parentheses or the subscripts. Once you've got them written correctly, the only way you can change them is with coefficients. I didn't do a fractional one yet. If we have time at the end, I'll do one. So now we're back to the original name of the chapter that we're studying, stoichiometry. Stoichiometric calculations relate not always masses, but for our purposes, we're going to start with masses. Masses of reactants to masses of product as the outcome. We can also look at it in terms of solution chemistry, and we're going to do that eventually. But we're going to start off simple. We're going to do mass to mass. So if we put so much mass of a reactant in, how much mass can we expect with 100% efficiency as a product? So first thing you want to do, actually before you balance the equation, you want to write everything correctly into your reaction. Then balance the equation. Then you convert any masses, you're given masses for your reactants, convert them to moles. Because in a balanced equation, if you've got masses on one side, you're stuck. You can't go anywhere in an equation with mass. You got to be moles, numbers. It's like there's a great wall. There's several great walls in there, and you can't get over or under them with mass. You got to use moles because they can burrow, I guess. And then we can use those coefficients also establish the molar ratios of reactants to each other and reactants to products, right? If we say, if we go back to say this one, where it has 2 calcium oxide and 5 carbons, for every 2 moles of calcium oxide, you need 5 moles of carbon. So if we have 4 moles of calcium oxide, how many moles of carbon do we need? 10, right? It's a ratio of 2 to 5, or 4 to 10, or 8 to 20, right? That ratio establishes a conversion factor that we may use in the future. Okay. So if you like schematics, I'm not going to spend time on that. Let's consider this one. This reaction where we have phosphorus, and this is one that's talked about carbon as allotropes. This P4 is an allotrope of phosphorus. You can also have a P8 or a P6, I think. But that's neither here nor there. This reaction is balanced for us, right? P4 plus 5, O2. I'm going to leave the phases out of it because they're not important right now. I'm just going to leave myself enough room to work. P2O5. There we go. Have you ever picked up a bag of fertilizer, nitrogen, phosphorus, potassium, right? The 3 major ones. And you look at it and it says, I don't know, 10, 10, 10. The first one is nitrogen, percent by mass. And that's just nitrogen. The next one is phosphorus, but it's not pure phosphorus, it's P2O5. So it's not 10% nitrogen, 10% P2O5. So it's actually less phosphorus than 10%. And the last one is potassium is K2O. And that has to do with, it's sort of a holdover from earlier days when the analysis was done to, in the outcome of the reaction that was used to assess the analysis of the fertilizer was in the oxides of the elements. So they got nitrogen, pure nitrogen out. They got P2O5 out of the reaction, so they just kept it that way. And they got K2O out of the other one. Anyway, this phosphorus reacts with oxygen to give you P2O5. If 6.25 grams of phosphorus, so I write that here, 6.25 grams of phosphorus is reacted, is burned, what mass of oxygen does it combine with? So what we're saying is that there's plenty of oxygen. We just want to find out how much oxygen was required. Right? So the question is, how many grams of oxygen? Okay. Well, in order to go from here to here and then to here, this has to be in moles, 6.25 grams, and we need to convert it like that. So 4 times phosphorus is 32, no, 30.97. So 4 times 30.97 is 4 times 36, 38. And is that right? 2 and yeah, 3. 3 and 12. 123.88. Okay, that'll tell us how many moles of phosphorus we're dealing with. 6.25 divided by 123.88 is, this is 5.045, and I'm going to use more significant figures so I have a rounding error, times 10 to the minus 2 moles. Okay, now that's moles of P4. We want to know how many moles of oxygen is required to completely consume all of that. So our ratio then, our conversion factor is P4 here to cancel moles of P4. Sometimes I write just P4 instead of moles. And then here is moles of oxygen. So the ratio is 1 coefficient and 5. Okay, that gets rid of this one and leaves us with this one. So 5 times that value will tell us how many moles of oxygen is required, which is 2.523 times 10 to the minus 1 moles of oxygen. Now we need to convert it back to grams because that's the question. What mass of oxygen is required? So we need moles of oxygen in grams. 1 mole of oxygen is 32 grams because 1 oxygen is 16 times 2. Okay. So does anybody get that for me? Let's see. We need 3 significant figures in our answer. See if you get the same thing I did. See, this minus 1 says that this is about 0.25 or 1/4. So what's 1/4 of 38 or 32? Well, half is 16 and half of that is 8. So it ought to be close to 8. 07? Yeah. Okay. 8.07 moles. Excuse me, grams. I remember the question. Grams of oxygen are required to consume all of that phosphorus. That's stoichiometry. And we didn't even go from here to there. We could take this and say, if we have this much oxygen available, we can convert it all to that. And then in that case, we would say this, instead of that, we would say 1 here and 2 P2O5. That would give us so many moles of this. Then we'd use that molar mass here to give us the number of grams of the product. Okay, so you can go to this place, you can go to that place, and we're still just 100%. This problem is, it's useful, but it's going to take some doing, and I don't think I have time to do it. Right, so go back to a previous video if you want to see how this is done. We need to write balanced equations. I think I've got it on subsequent slides, so I can move through it kind of quick. This is the balanced equation for methane combustion, CH4 and 2 oxygens, carbon dioxide and water. Then ammonia combustion and oxygen. is this balanced equation. And this one, we did use a trick of fractional, I think. Maybe, maybe not. And then we say, what mass of ammonia would produce the same amount of water as 1 gram of methane? So what we're saying is, uh, these masses are equal here and here. And we want to find out what mass of ammonia would give us the same amount of water. Right. So we work our way down this end to find out the mass of water, and then we take that mass here and work our way backwards to the ammonia. Okay. So that's the question. We need to balance the equations. There's the first one balanced. There's the second one balanced. And I used my budget method to do that. Then we work through 1 gram of methane is 10 to the minus 2 moles of methane. And then we convert that to how many moles of water would be produced. Right. In this case, we're saying we've got plenty of oxygen. Right. That's not limiting. So we produce 0.1246 moles of water. Well, we don't have to go all the way to grams. Just say, all right, that's the same number of moles of water for the second equation, and work our way backwards to the ammonia. So now we know how many moles of ammonia we need to produce the same amount of water, and we just make the conversion to mass. So 1.42 grams of ammonia will produce the same amount of water combusted as 1 gram of methane. Okay, and then the last one is a concept of limiting reactants. I mentioned earlier that up to this point, we're dealing with 100% efficiency. And of course, that never happens. So we have to deal with, it's kind of like error, right? There's nothing we can do about the error except to account for it. So we're going to account for efficiency by looking at 2 things. One is the limiting reactants. The reactant that runs out first, if you have, say, a balanced equation and you have 2 reactants on it, and you're given exact amounts of each ones that are introduced into the reaction, then 99.99% sure that one of them is going to run out first. Right? The one that runs out first is the limiting reactant. So how do we determine what that limiting reactant is? There are a number of ways to do it. This is just a schematic. I'm going to skip this. This just says this is the stoichiometric mixture. This is an idealized reaction in which you have exactly the right amount of nitrogen and hydrogen molecules to make all ammonia. That's called stoichiometric mixture. And in practice, it never happens, right? Because there's always measurement error. Okay, this is a case where we have a limiting reactant, and the limiting reactant is the one that's used up. And notice we've got blues left over. Those are nitrogens. We've used up all the hydrogen, so the hydrogen is the limiting reactant here because it's all used up and we got leftover. That's the excess. Limiting reactant is hydrogen, excess is nitrogen. Okay, I'm going to skip this too. We can't simply add the total moles of all the reactants to decide which reactant makes the most product. What we have to do is the surefire way to determine the limiting reactant is to say, if we're given so much of this reactant, say, how much product can it make if we use it all up? And then go to the second one and say, how much product can we make with this one if we use it all up? The one that makes up the least amount is the limiting one. Okay? That's a surefire way to do it. You can't go wrong with that one. And then here's the concept of percent yield. Right? This takes into account the actual experimentally determined yield from a reaction. we can calculate the theoretical yield because we know what we're putting into it, and we can say this is what we would expect if everything is converted. But we actually measure the output, the yield of a product, and we ratio that to the theoretical yield, and that's percent yield. For this example, and I'm over. It's 4 o'clock, right? 10 minutes over. Yeah. I don't know if I have this one worked out or not. Yeah, there we go. So for this one, we have a balanced equation. What mass of P4 is needed to produce 85 grams of PF3 if the reaction is 64.9% yield? So what we need is, in order to make the calculations work, we need to know, all right, what would the theoretical yield be? And that's what this conversion is. 85 grams is what the actual yield is. We want to know what would be the theoretical yield. So 64.9% is 64.9 over 100. That's what we're saying. And we flip it so that we can cancel the actual and leave us with a theoretical. Another way to look at it is 85 divided by 0.649, and that'll give you the same number. Now that we've got the theoretical yield, we can work our way backwards to say, all right, this is what we need to start with to give us the theoretical amount, and then with the 64.9% efficiency, we actually only get 85. So we got our theoretical. Now we can work our way backwards. Right? That much PF3 is converted to so many moles of PS3 because we can't go anywhere with mass. So we got to take PF3, our theoretical amount, convert it to moles. So that 87.97 grams is the molar mass, right? 3 fluorides plus 1 phosphorus is 87.97. So we convert to 1.489 moles of PF3. Now we can use our coefficients to ratio 1 mole of P4 for every 4 moles of PF3. Cancel the PF3s, leave us with P4s. Now we know we have to start off with 0.3723 moles of P4. So we calculate, all right, what's P4 molar mass? 123.9. And we flip it so that the grams are on top and the moles are on the bottom. We cancel the moles, and that gives us 46.1 grams of P4. That's what you have to start with to end up with 85 grams of PF3 with 64.9% efficiency. That's the kind of thing that chemical engineers do day in and day out. They try to improve the efficiency of their reactions. And I don't know what it is now, probably the same. Chemical engineer, a bachelor's chemical engineering degree is a pretty good starting salary. That's it.